In this video, we're going to look at a technique called tree diagrams. Let's jump into our first example. A shipment contains 9 good and 2 defective items. Items are selected one at a time without replacement until a good item is found. First thing we're going to do is draw a tree diagram. All right, well, let's come up with just a shorthand notation here. Let's say G represents good, D represents defective. So you use a tree diagram when you want to represent visually 2 or more things that could happen. So we're going to have a tree diagram here like this, representing the 2 possible scenarios that can happen first. What we're doing is we're just selecting an item from this shipment. So our item could either be a good item or it could be a defective item. Those are our 2 choices. Now we're told in the problem we do this selection until a good item is found. So if we were going along the top branch of the tree and we got a good item, the process would stop. But if we were actually on the bottom branch of the tree and we had chosen a defective item, then we're going to make a second choice. So from there, there's going to be another branch. And again, we could get a good item or a defective item. So what we're going to do is we're going to start putting the probabilities onto the branches of this tree diagram. And so what the tree diagram does is it just helps us keep a lot of different probabilities organized. So let's look back at our information about the shipment. We know the shipment had 9 good and 2 defective items. So let's put some probabilities on here. At the beginning of the selection, there were 11 items in the shipment. 9 of them were good, so 9 out of 11 probability that we got a good item at the beginning, 2 out of 11 probability that we got a defective item at the beginning. Now let's say we went along the bottom branch of the tree here and we actually chose a defective item. We now need to update what our shipment looks like because we've pulled one of the defective items out of the shipment and we said that we're doing this selection without replacement. So once we choose an item, it's not going back into the box. So let's think about what kind of items are in the box. There would still be all 9 good items in the box, but there would now only be 1 defective item in the box. So that's what our shipment looks like at this point. And these are the numbers that we're going to use for the second branch of the tree. So when we now make our next choice, probability of getting a good item will be 9 out of 10. Probability of getting a defective item, 1 out of 10. And if we chose a good item, the process stops because we said we're going to stop the selection once we get a good item. If we chose a defective item, we would continue. And so again, there's going to be another branch of the tree representing possibility of getting a good or defective item. So we should do one more update here and just write down what our shipment looks like at this point. So suppose we've gone along these 2 bottom branches where we got a defective item and then another defective item. What does our shipment look like now? Well, now there's just 9 good items in the box, no defective items. So probability of getting a good item on our next selection, 9 out of 9. Probability of getting a defective item, 0 out of 9. So now that we've put some work into that tree diagram, let's do some probability calculations based on the tree diagram. So part B, we're going to find the probability that 1 item is selected. So if we look back up at our tree diagram, if our first item had been good, then we would stop the selection. So probability that 1 item is selected, 9 out of 11. Part C, let's find the probability that 2 items are selected. So let's look at our tree diagram and figure out how that could happen. So if we chose a defective item and then a good item, that would be a way in which we would end up with 2 items in total. And to get the total probability of this happening, we need to multiply the probabilities because we're saying we're getting a defective item first and then we're getting a good item. And that word "and" prompts you to multiply the probabilities. So we'd go 2 over 11 probability of getting the defective item times 9 out of 10 probability of getting the good item after that. You can put that into your calculator and just turn that into a decimal. So 0.16. And final part here, let's find the probability that 3 items are selected. So let's look at our tree diagram and figure out a way in which 3 items would be selected. Well, we'd have to have a defective item and then another defective item. Then once we get to here, really the only possibility is of getting a good item, because if you notice, this probability here is 0. So that represents something that can't happen. You can't get a third defective item. So choosing 3 items means you get the order defective, defective, and then good. And the word and, again, is just going to prompt us to multiply all of these probabilities together. So we're going to go 2 over 11 times next probability was 1 out of 10 times next one was 9 out of 9. Can type all this into our calculator and we get about 0.02, 2% probability of selecting 3 items. So that's our first example of using a tree diagram to store probabilities and to calculate probabilities. Second example, at a college, 3/5 of students are in business, 2/5 of students are in technology. Half of the business students have a job. 1/3 of the technology students have a job. We want to find the probability that a student is in business and has a job. Well, first thing we're going to do is draw a tree diagram. It will be helpful not only for this calculation, but for some of the upcoming calculations in this example. So let's think about what our tree diagram should look like. We'll think about what the first choice is. So first thing we're told is just the proportion of students that are in the 2 different programs, business and technology. So first branch, a student is either in business or in technology. And then once we know whether we're talking about a business student or a technology student, we can talk about the probability that they have a job or not. So the second set of branches would represent job or no job. And we'd have the same kind of choice for the tech student, job or no job. So let's see if we can put all the probabilities on here. We're told that when we look at all the students, 3/5 of them are in business, 2/5 are in technology. So 3/5 probability that a student is in business, 2/5 technology, or 2/5 probability that they're in technology. And then from there, we've got the job information. So half of business students have a job. Notice that our sample space here is the business students. So we have to be sitting at this point in the tree diagram if we're talking about business students, and then say, now what's the probability that that business student has a job or not? Probability that they have a job, half. Therefore, probability that they have no job, 1/2. See, these probabilities are going to add up to 1 because a business student either has a job or does not have a job. Then we're told that 1/3 of technology students have a job. So our sample space now is the technology students. So imagine we're sitting here looking at a technology student. 1/3 of those tech students have a job, or you could rephrase that as 1/3 probability that a tech student has a job. Therefore, 2/3 probability that they have no job. So again, these probabilities have to add up to 1 because a tech student either has a job or does not have a job. So that's the actual drawing of the tree diagram. Now let's answer the question that's being asked. We want to find the probability that a student is in business and has a job. Well, the word and is just going to prompt us to multiply. So we're just going to look at our tree diagram and trace along the appropriate path. We want them to be in business and we want them to have a job. So the answer is going to be 3/5 times 1/2. And if you put that into your calculator, 0.3. Now part B, let's find the probability that a student has a job. So if we map this out in words, the possibilities would be that a student is in business and has a job, or there's a completely different possibility that they are in tech and have a job. And we know from our discussion of counting that the word and is going to prompt us to multiply and the word or is going to prompt us to add. So let's see if we can fill in the details. So for business, 3/5 probability that a student is in business. And then from there, once we know that they're a business student, probability is half that they have a job. So we're just multiplying along that path there, 3/5 times 1/2. But then we're going to be adding on a completely separate possibility, which is that the student is in tech and has a job. So 2/5 times 1/3. And you can put all of that into your calculator. I'm going to round that off to a few decimal places because we're going to do a follow-up calculation with this. So that comes out to about 0.4333. So because we're going to be working with tree diagrams quite a bit in this section and the next section, let's see if we can write down in terms of the tree diagram how we actually did this calculation. So what did we do? We multiplied along each path. So to get the probability that a student was in business and had a job, we multiplied business and job, because and is the key word for multiplication. And then if there are multiple paths that lead where you want, for example, in part B, we were trying to find the overall probability the student has a job. There were a couple of different ways to get to job. We have to sum. So let's say sum all paths. So you're summing them or adding them up because they're representing different possibilities that can happen. The keyword or tells us to do an addition. Let's finish off this example with a part C. So let's find the probability that a student is in business given that they have a job, right? So this is an example of a conditional probability. Let's see if we can write it down symbolically. So we're given that they have a job. Remember, the given information goes at the back of a conditional probability. And what we want is the probability that they're in business. So probability, business, given, job. Let's remember our conditional probability formula. So you go probability of this and that, business and job, divided by the probability of the given information. So dividing by probability that a student has a job. So part C is really just going to use the two numbers that we calculated in part A and part B. In part A, we calculated the probability that a student is in business and has a job. We found that to be 0.3. And in part B, we calculated the overall probability that a student has a job. We found that to be 0.4333. So that's actually why I carried some extra decimal places in part B, just so that we could do this follow-up calculation. So if you put that into your calculator, it comes out to about 0.69. So about 69% chance that if a student has a job, then they're in business. So here's a clean version of the tree diagram that we were working with in that example. And let's write down the probability that we just calculated. So we calculated the probability that a student is in business given that they have a job. So this type of conditional probability is called a backwards probability because we're asking for the probability that the first event happens given that the second event happened. So let's take a look at our tree diagram and understand why that should be true. So we're told that we're looking at a student who has a job, meaning we know that they either represent this path here, business and job, or they represent this path here. We have information about the second thing. We know they have a job. And the question that we're asking is about the first thing. We're asking, now, how likely is it that they are actually on the top path and they are in business? So that's a backwards probability. We're saying we know the second thing is true, but how likely is it that the first thing happened? And tree diagrams are especially useful for helping us calculate these type of backwards probabilities. So let's look at another context where these backwards probabilities come up quite often. Let's look at the situation of testing for a disease. So this could be something like testing people for the flu, for example. We'll think about the first possibility, whether a patient has the actual disease, so has the flu, or whether they don't have the disease. From there, a patient may test either positive or negative for the disease. So let's think about what this plus and minus represents. When we say plus, this means a positive test result, and what that means is the test indicates the disease. Now remember that medical tests are not perfect. Just like anything in the real world, not perfect. There can be human equipment error, etc. that causes occasional errors in the test. So to say the test indicates the disease is not quite the same thing as actually saying that the patient has the disease. Similarly, the test could be negative, and that would mean the test indicates no disease. So that probably means that the patient doesn't have the disease, but again, tests are not 100% accurate. Now, if a patient doesn't have the disease, then again, the test could come back positive or negative, indicating whether the test indicates the disease or indicates no disease. So that's the structure of the tree diagram when we're talking about medical testing. Let's say we're told 5% of patients have a certain disease. The false positive rate is 2% and the false negative rate is 3%. Okay, we'll figure out what these things represent by drawing a tree diagram. So let's think about the structure of the tree diagram for medical testing. So first decision is just whether the patient actually has the disease or not. So patient has the disease, or we could just say disease for short, versus no disease. And then from there, we're talking about whether the test detects the disease or not. So the test can either detect the disease, which would be plus, or a test does not detect the disease, which is negative. Again, if there's no disease, tests could come back positive or negative. Remember that tests are mostly accurate, but there can be occasional errors due to human error or equipment error or other reasons. So let's see if we can put our probabilities on here. First thing we're told is that 5% of patients have a certain disease. So that's referencing the first set of branches. 0.05 probability that a patient has the disease, and therefore 0.95 probability that the patient does not have the disease. So these numbers here should add up to 1. In other words, they should add up to 100%. Okay, now let's talk about this false positive rate. So false positive, well, it's a positive result that is false. So it's a positive result that's wrong. Okay, so let's think about where the false positive would be in this diagram. So since it's a positive, it's either this one or this one, but which one of these is wrong? Well, if the patient does not have a disease and the test comes back positive, that's a false positive. So when we say the false positive rate is 2%, we're saying this probability here is 0.02. And that information then helps us figure out this probability. This one would have to be 0.98 so that these guys add up to 1. So let's just do a double check on that and make sure that makes sense. So let's say you've got a healthy patient who does not have disease, 2% probability that the test is going to make a mistake and actually tell them that they're positive for the disease. 98% probability that the test will do the correct thing and say, yep, you're negative for the disease. Okay, now let's talk about the false negative rate. So again, the false negative is a negative. So it's one of these two numbers, and it's the one that's false. So if someone has a disease, but the test comes back negative, that would be a false negative. So that would be this circled number here. And we're told the false negative rate is 3%. So that's just another way of saying this probability is 3%. And once we know that, 0.97 probability there, so that these set of branches add up to 1 or add up to 100%. So again, let's do a double check on that and make sure that makes sense. So suppose you have a patient who has a disease, someone who actually has the flu, for example, 97% probability that they're going to test positive, only 3% probability that they will test negative. So all these numbers seem to be reasonable. So with that, we can get into an actual applied problem. So let's say 3% of students have the flu, and then we've got some information about what proportion are going to test positive and negative. The probability we want to calculate, probability that a person who tests positive actually has the flu. First thing I'm going to do here is write down the probability that we're trying to calculate. So let's write this in symbols. So probability that a person who tests positive, so that's what we know for sure, that they're testing positive. What we wonder about is the probability that they actually have the flu. Okay, so remember when you're writing down a conditional probability, you put your given or known information at the back. So we know they're testing positive. The question is about whether they actually have the flu or not. So there's our conditional probability. Now let's start to map out what our tree diagram looks like. So based on our discussion about medical testing, the first set of branches represent whether the patient has the disease or not. So first decision is whether they have the flu or no flu. And then from there, you can talk about how likely it is that the test will come back positive or negative. So that's going to be the structure of our tree diagram. Now let's look for a second at the probability that we're trying to calculate. It has the structure probability of the first event given the second event. So this is what we were calling a backwards probability. So just for a visual representation of the backwards probability, you could say, you know, the second thing is happening. You know they're coming back positive for the flu, but your question is about the first thing and wondering, well, do they actually have the flu or not? So what we're going to do here, label all the probabilities onto our tree diagram. So let's see what we know. 3% of students have the flu. So that's 0.03 probability that someone has the flu, 0.97 probability that they do not have the flu. So those two branches are going to add up to 100% or add up to 1. Okay, then of the people with the flu, 96% test positive. So assuming you're looking at someone with the flu, 0.96 probability that they will test positive, and therefore 0.04 probability that they will test negative. So these numbers are going to add up to 1 because you're talking about a person with the flu and they're either going to test positive or they're going to test negative. And then finally, of people with no flu, 95% of them are going to test negative. Okay, so assuming you're looking at someone with no flu, 0.95 probability that they're going to test negative, and therefore 0.05 probability that they're going to test positive. These numbers will add up to 1 because someone with no flu will either test positive or test negative. So now that we've got all the numbers in the correct places, it's just a matter of using our conditional probability formula. So I'm going to write out again the probability that we're trying to calculate. We want probability that someone has the flu given that they test positive. So according to our conditional probability formula, that means doing probability flu and positive divided by probability of the given information. So just probability positive. So if we want flu and positive, the word and is just going to prompt us to multiply along the appropriate branches. Flu and positive, we're going to go 0.03 times 0.96. Okay, and then that has to get divided by the probability that a patient is positive. So I've just redrawn the tree diagram over on the side here so that we can see it clearly while we're doing our calculation here. So we want to divide by the probability that a patient is positive. Okay, so now this is where we need to think about all the ways that a patient can be positive. They can have the flu and be positive, or they can have no flu and be positive. So if you think about your keywords and or, that's going to mean multiplying 0.03 times 0.96, that's flu and positive, or is going to prompt us to add no flu and positive would be 0.97 times 0.05. And because we're going to be dividing by this entire expression in the denominator, just from the point of view of the calculator, quite important to have brackets on there. Otherwise, the calculator will make an order of operations error. So whenever you have a couple of things added together in the denominator, you're going to want brackets around that denominator. So we worked out this denominator here just by thinking about our keywords and or. An alternative way of thinking about this is just to frame this in terms of the tree diagram. You could say multiply along each path. So flu and positive get multiplied, for example. And then if you're trying to incorporate multiple paths, then you're going to sum the paths, sum all the paths. So since there are two ways for a patient to end up positive, you're going to see two terms in that sum. So that's just another way of rephrasing the idea that when you say and, you multiply, and when you say or, you add. So if we put all this into our calculator, we get about 0.37. So let's interpret that. That's 37% of positive patients actually have the flu. Now, does that seem surprisingly low to you? To me, that seems low. I would expect, okay, of positive patients, I'd be happy if, say, 90% of them actually had the flu or 95% of them actually had the flu. This number, quite low. So let's talk about why this number is so low in this context. And that happens when the disease is rare in the population. So in our example, only 3% of people had the flu. Therefore, that disease could be considered rare in the population. And when that disease is rare, the test error becomes significant. So if we actually repeated this problem and made it so that now 30% of students have the flu instead of just 3%, we'll see a much more reasonable probability. So let's just run through that quickly. So now let's assume 30% of students have the flu. We'll assume the same false positive and false negative rates as before. So all that we're changing is just these initial probabilities of having the flu or not having the flu. So now if we redo the calculation, which is calculating the probability that someone has the flu, given that they test positive, if you feel like doing another practice calculation here, you can confirm this comes out to about 0.89. So that's much more reasonable. You could say 89% of positive patients actually have the flu. So we used tree diagrams to calculate probabilities, and we saw that tree diagrams are especially useful for calculating backwards probabilities. So that's our video on tree diagrams. Thanks for watching.